I guess I'm going to start now. Hello, everybody. I'm Philipp Huismann from DigiCo. I'm a data scientist, and some time back, I was actually a mechanical engineer in the energy sector as well, and worked a lot on energy research, energy system analysis, energy system modeling and simulation and everything, and then drifted more and more into geodata and settlement classification. And I had the pleasure to work on settlement classification basically the last months. And today, I will give a talk about what's the current status of the energy transition, especially the heat sector, and generation of new spatial units for our use cases, our data product, and the clustering of settlements. So let's start with the current status of the energy transition in Germany. Here we have the electricity sector. As you can see, this pink line indicates the current share the electricity is provided renewable, and it's above 50% already, which is pretty good. And you can already also see that the total energy consumption is decreasing here as well. So this is really nice, and this is obviously because wind power and photovoltaics have increased by a lot. As you can see here in this GIF, you can see it's increasing quite a bit in the recent years. So this is really nice. On the electricity sector, it's going quite okay. It could be better, but it's a good start, I guess. If we go to the mobility sector, it's kind of a little bit of a different story. It's more or less flattened out. We only have 7% renewable here, and important to say it's not just the personal vehicle space here. It's logistics, transport of goods by air and shipping. So not just your own electric vehicle. If we go to the heat sector, we can see an increase of the renewable share, but it's not really comparable to the electrical sector. This has a couple of reasons, and I will delve into the heat sector now a little bit more. As you can see here on the left side, there is a distribution of technologies in the heating sector in Germany, and you can see here a lot of gas and oil, non-renewable. And if anybody is from Denmark, it might be a little bit surprising. We have a very dense population and building structure, but our district heating sector only is 14%. In Denmark, it's, I think, above 80%. Additionally, the heat pumps distribution here is also quite low and should be probably a lot more higher than just that. So we have to switch from these gas and oil technologies to more like district heating and heat pumps and maybe other technologies like biogas or anything like this. Additionally, we have a pretty old distribution of the heating technologies currently in use. If you see here, 33% of the heating technologies are older than 20 years. And if you think about how long will I have to use my heating technologies in the buildings, it's usually you should think about new technology when you have a 20-year-old heating system. And at 30 years, you should definitely replace it. So we have a large share of technologies that have to be replaced now, and the consumers need to know, okay, what should I build, what should I buy in the next couple of years or even months, and to summarize the heat transition in Germany, large share of non-renewable heating technologies, significant share of heating systems that need to be replaced, heating technologies currently tied to infrastructure like gas and we need to integrate more potential renewable energy sources. And for these purposes, the German government decided to, by law, make it mandatory to do a municipality heat planning, meaning like every municipalities, more than 11,000 in Germany, have to make a plan. How is the heat coming into my home? And yeah, this has to be done. To be fair, a couple of municipalities, especially in the southern west of Germany, already did that or are currently doing that. But there are still a lot of municipalities that have to do that, yeah. And maybe you're asking now, what is geodata doing? What is going on with geodata here? It's relatively simple, to be fair. Like, what is the status quo? Where are the old buildings? What technology is where? Where's the infrastructure? Where's the current district heating system placed? What technology be used? Where are renewable heating sources? Where are large heat consumers? Very important. And what is the future heat demand? And at DigiCo, we basically build a digital twin of our heating system in Germany, meaning we have geospatial data that is detailed about technologies, building age, renovation status, building type, but also stuff like what is the how much money how much money people have to spend in the area. So very geospatial driven, and also modeling, scenario models. We can do simulation with parameterization of a municipality for 2030, 2040, 2050, and the consumers can like say, okay, have more heat pumps or less heat pumps, more district heating. And results can be, for example, what you can visualize here is for this municipality, it's a relatively big one. As you already saw a couple slides earlier, the gas is currently the largest technology here. And we can already also calculate the share of wallet, meaning how much money does every consumer spend on heating of their income. Additionally, for the municipality heat planning, we also need new spatial units. This is mostly building blocks and sub-areas. Building blocks are basically just an aggregational unit that is limited by infrastructure, such as natural boundaries, rivers, lakes. And they are just great for visualizations. And as a bonus, when you process them correctly, you can merge building blocks to always have enough buildings so that you can integrate real data. And this is really important when you do municipality heat planning, because you don't want to like have on a single building the actual real energy consumption. On the other side, sub-areas are then aggregated from building blocks, and they are like homogeneous building structures aggregated from building block level, and they are great for heat planning. So you can look at a sub-area and say, okay, there it should be district heating, there are heat pumps and everything. And this is what I'm going to talk about now. The tools I used for that is, it's not a surprise probably, GeoPandas for geodata processing, Pysars for spatial connectivity. This is really useful. And MomPy feature generation, like building density and such things. And last but not least, scikit-learn for clustering and inference. Speaking about the building blocks, the process is relatively simple. I use our building data set. I use infrastructure and natural boundaries for an OpenStreetMap, such as rivers, streets, not every street, not every track, but most of them, and land use data from current land cover. And I merge them all together and basically remove empty geometries that have been created by MomPy with enclosures. Maybe some of you know that. And then in the end, we have the building blocks here, but these geometries I can't really use already, so I have to post-process them. First of all, we need to achieve data protection requirements, meaning I merge building blocks together that have too low of building count, and I do this by having a balance in merging goal, meaning I want a low number of buildings in total if I merge two blocks, and I want a higher shared boundary. And I do this automatically for the whole municipality, and then I merge these building blocks. On the other side, I improve the geometries, because sometimes when you use the enclosures, you get like very large geometries, and this is obviously not perfect. And even sometimes today it still remains, because I have to identify these first of all. I use I calculate the building distances between the buildings in the block, and if they're too large, I know, okay, I have to adjust the building the block geometry. This is basically what's happening here. And then when I have the building blocks, I can already use it for visualizations. For example, here we have 2023 result of our the status quo of today of DHN in a large city here in Western Germany, Recklinghausen, if anybody knows. And on the right side, our simulation result of 2040, now of some arbitrary scenario where we can see the district heating share increased by a large margin here in this municipality. And on the right side, you see basically how much energy is provided by each technology. As you can see here, this is DHN, meaning district heating. And you can already also see the heat pump share increased by a lot as well. When we have these building blocks, I can start with the sub-areas method. And this method I used can be divided basically in six steps. First of all, I identify settlements within the municipality, because there are sometimes municipalities that don't really have a combined settlement structure. Sometimes they are just little settlements within this municipality. Then I separate this municipality with major infrastructure, natural borders and such, compute features for the clustering later, compute spatial connectivity, and cluster within spatially connected building blocks. And in the end, I aggregate the blocks to get nice geometries for the sub-areas. Okay, for the first step, identification of settlements. This is really important because if I don't do this, I get a great big settlement cluster, and then I perform the clustering on it, and I actually want to separate sometimes these settlements. If you can see on the bottom right here, if I don't do this, I might be clustering on all of this, but I actually need to split it up right here. And this is why I use HDB scan and the highest silhouette score to find the best configuration of settlements in the municipality. And this municipality I'm showing right here is pretty easy for HDB scan generally. But if we go to more complex municipalities, for example here Bonn in Western Germany, this is a lot more difficult. For example, this right here I marked here. Where's the has been identified by HDB scan as basically a small settlement within the municipality, and this was really important so that I can get one sub area for this area, and it's not included in somewhere else in this municipality. When I have these settlements, I divide them again because we need to separate them from major infrastructure, these sub areas. I don't want to have a sub area that spans across a river or a large road, because this is very important when you think about what technology to use where. So I use, like I already said, OpenStreetMap for this, highways, main roads, rivers, lakes, and everything, and get an ID for each building to know where it is. For the feature selection or creation, we need to find homogeneous areas, meaning we have to capture the spatial building structure and the individual status of each building. And most important for heat planning is building density, building age, and building type. Building density is very important basically for district heating, because if the distances between the buildings are close, you have less pipes you have to buy or put into the ground. You have less heat loss. Well, on the other side, a dense building structure is bad for heat pumps, because if you were listening to the presentation before, the noise emissions are a big factor of this of heat pumps. Additionally, the building age. When you think about how much heat each building consumes, you need to know that, and the building age is a very good indicator about that. And another building type is also very important, because if you have very large buildings that maybe have a small footprint, you might not use heat pumps, for example, as well. Additionally, I use tessellation on buildings from MOMPI to compute a available floor area which is very useful to get the building density. As I mentioned, the clustering algorithm is only applied within spatially connected building blocks. So, like I said, I don't want to have an agglomeration of building blocks above a large road, for example. This is done using Pysal for touching building blocks. Sometimes you have to buffer distances between building blocks so that they are connected. And then you can see, as you can see here, we have this building, this agglomeration, and on this side, this agglomeration. And for each of these agglomerations, I will perform the clustering. Speaking about clustering, where I identify homogeneous areas, for this I use the agglomerative clustering from sklearn and the spatial learns I previously computed. The biggest thing here is to automatically find the right numbers of clusters, because with agglomerative clustering you need to add the number of clusters. And this is done not using the original silhouette score, but the past silhouette score. This is, if you don't know the silhouette score, it's silhouette score is sorry. The silhouette score looks at your clusters and looks at the other clusters and how far they are separated. You want to have dense clusters and that are very much separated from the other clusters. And the path silhouette score also adds the weight to the silhouette score, the spatial metrics, I mean. And this was really, really useful. If you look at the bottom right, I have the silhouette score and path silhouette score median for each cluster, and you can see the highest normal silhouette score is at 2. And this is actually not the not the cluster size I actually want for this settlement. I want the 3. If you like here we have a old settlement and here a relatively new one. You can see it in the data as well on the right side. And on the left side you have another building age distribution. And using this path silhouette score, you get a 3 instead of the 2, and this is really, really nice because we get more separated clusters that we actually want. I added another slide here to see the process. Like I go through all the clusters, usually only to 10, because we don't want to have too small of clusters, even if the silhouette score is big. If the silhouette score is really nice, then we will not. If the silhouette score is really nice for like 10 clusters, then we will not cluster these and use the area as one, because then it's usually just 2 separated in this region. On the right side, you see as a dashed line the usual silhouette score. Here, the blue one is the usual one, the best one, and for 2 clusters, and the orange one right here is for the second best one and 3 clusters. And you can see if I use this normal silhouette score, I would get use this one, and this would mean I get only this separation here. But if I use the past median score, I get this one and get the one I actually want, like the 3. When I have done this clustering, and we have to remember I do this for all of municipalities in Germany, so this has to be robust. You have to remember that sometimes you get a municipality where this will not work. Sometimes you have a settlement where you actually want the 4, not the 3, and it's quite a fun experiment to find the best metric here that maybe fits all the municipalities sometimes. Then in the end, I take all these blocks and aggregate them to polygons by buffering and merging, stripping off any overlaps, filling the holes, so that I get really nicely defined sub-areas. Here you can see one of the results for the municipalities I showed a couple of pages ago. Here we have a settlement structure that is probably the center of an old village. Here we have a settlement structure that is newly added to already existing settlement. And we also define, find the industry and trade settlements within this municipality. These industry and trade settlements are identified once by our building data set, where we know each building, what type is it, but also using current land cover, because this can sometimes even improve the data quality in this part as well. Yeah, limitations and outlook. Sometimes there's missing building data, especially for new developments. We obviously can't really always have the newly built buildings in our data set. Missing infrastructure, mostly from OpenStreetMap. This can obviously happen if there is a new development as well. So then we obviously can't cluster in these areas as well. Large non-divided settlements are a struggle as well, because if we have, for example, a very large inner dense city, then we use the agglomerative clustering there, and there might not actually be any clusters we want. So we should not have any clusters in this, and have just this one big sub area. Additional computational speed, especially tessellation, which when I applied on the whole building data set, for example, of Berlin or Munich, this can take quite a long time. And what can really help is already separate these buildings beforehand, so that you only use the tessellation in some part of the building data set. HGB scan is obviously sometimes quite computational intensive as well. Yeah, we will improve the identification of the optimal size of clusters. This is more or less ongoing as well. It's already quite a good result, but I think there's always room for improvement. And we will implement this in our heat planning framework, so that we can give our customers a nice tool to visualize their decisions, to find regions where they have to make decisions, where they should make decisions, and yeah. Thank you for your attention.
Thank you very much. It's time for questions. Are there any questions?